All right, everybody. Since we're not going to be in class, uh, I'm going to go ahead and make this video for our lecture, and that's what we'll call our Friday. Okay, so we're at gravitational forces. So again, gravity exists between every object that has mass. Uh, so even the smallest things have a gravitational force with each other. It's just very, very tiny. Like, for example, the gravitational force between two automobiles is about as it's about as strong as the weight of a mosquito. So you have to take into account where you talk about gravity and where you don't. Between planets, between stars, much, much stronger. So over here on the left, you can see Newton's universal law of gravitation, one of them in the vector form, one of them in the magnitude form. So the vector form has the standardized r hat unit vector. And really what that's going to be is that's just going to be a unit vector directed along the axis connecting the two centers of mass. And that's one of the things that's important about gravitational force is everything is measured from the center of mass. So I don't know, let's say we have going to have one, I don't know, planet, star, whatever there. You have another one here. So the center of mass for a sphere is going to be right at the center. Okay, and then the connection between the two is going to be there, and so your r hat will be directed along that connection between the two centers of mass. Um, and when let's say you look through your physics textbook and it talks about the separation between like the Earth and the Moon, that is the separation between the two centers of mass, not necessarily surface to surface. Also notice that we have the universal gravitational constant that'll come into play. Um, but these two masses are going to produce uh, gravitational forces on each other. So we have mass one, mass two, and the gravitational forces. So this is going to go back to how we were talking about how to read forces. You're going to have a gravitational force. Yeah, let's make that easier to see. That goes that way. And one that goes that way. Now, gravitational forces they come in pairs. So here, you can say that this one is force 2, 1. That's the gravitational force of mass 2 on mass 1. And this one is force 1, 2. That's the gravitational force of mass 1 on mass 2. And since these come in pairs, this means that you get an equal and opposite force. So for gravitational forces, they're going to be equal and opposite. Okay, so let's uh, let's think about a problem. I want you to pay attention to this one because this is something you're going to end up doing in your assignments. This is just going to be a mathematical exercise. We're not even going to look for a specific number. We're going to look for equations that would give us numbers. And so you will be doing a bit of this semester because remember, physics, the real goal of physics is to be able to model the universe around you mathematically. So the mathematical models are central to what we're trying to learn. Okay, so here, find altitudes above Earth's surface where Earth's gravitational field strength would be first 2/3 and second 1/3 of its original value at the surface. So we've been talking a little bit about weight. And so the way you can think about that is, say, an object's mass inside of the Earth's gravitational field. And so if you go back up and you think about these laws of universal gravitation, we can pull the gravitational field out of that. So, for example, for Earth, our gravitational field is usually going to be denoted as G, and it's going to be a constant. And the field is going to be the gravitational constant, mass of the Earth, over the radius of the Earth squared. Okay, so essentially what we're looking for is a new field strength, and what altitude and what height does that occur at? So we're going to call our new gravitational field G prime. And that's going to be some factor n times the original gravitational field, where at one point n is going to equal 2/3. Oops. And at the other point, it's going to equal 1/3. Okay, since we already have a format for our gravitational field, our new gravitational field is going to equal G, mass of the Earth, over r squared. And this time, r is going to be the radius at the new altitude h. So that's, you really think that's going to be the radius of the Earth plus h. Okay, so let's start putting everything together here. Okay, so we have an expression for g, we have an expression for g prime. So let's say we want to get to an expression for h. That's what we're going for. What is the altitude? What is the height that's going to generate this new gravitational field? Okay, so the first thing we can do is we can solve our equation, our second one, and say, well, n is going to equal g prime over g. Then I can plug in, that's going to be g, mass of the Earth, over r squared, over g, mass of the Earth, over the radius of the Earth squared. Let's see, your g and your mass of your Earth are going to divide out. So we're going to have 1 over r squared over 1 over r e squared. And when we have fractions like this, when you have fractions inside of a fraction, so in this case, for example, your re squared is going to flip up to the top and your r squared is going to go down to the bottom. And this is going to end up being and so our n is going to be re squared over r squared. Now remember that we said that our new radius r is going to equal our altitude h plus re. So let's go ahead and solve for r. Okay, so if we solve for r, we're going to get r squared. It's going to be the radius of the Earth squared over the value n. And then we're going to go ahead and take the square root of both sides. Okay, now, how can we break this up? So you know that if you have a square root of the whole thing like that, we can do square root over square root, which is going to give us the radius of the Earth. Oh, whoops. Over the square root of n. And again, you could make more sense out of this if you're having trouble with the square root. Remember, you can always say that the exponent of 1/2 is the same thing as a square root. And you know that an exponent then will distribute into the equation. So you end up with the same thing, radius of the Earth over square root of n. Okay, so let's go ahead and substitute the h plus re in for our radius, our new radius. So we're going to have h plus re equals re over the square root of n. Okay, so then I'm going to go ahead and say h is going to be r sub e over the square root of n minus r sub e. And then I can pull out the r sub e. And now what we have here is we've now derived, we solved for the altitude at which these that will shift our gravitational field based off our value of n. So it's going to help us solve for that altitude that'll give us our new gravitational field. And this is a generalized equation. And now we can put in our various values of n and see what this will actually come out to be. So let's look at part A. N equals 2/3. All right, well, h is going to be the radius of the Earth. One over the square root of 2/3 minus one. Okay, how much space do I have? I have plenty. Okay, that's going to be the radius of the Earth. And again, remember that's square root of 2 over the square root of 3 and minus 1. We're going to bring that square root of 3 up to the top of the fraction. And for part A, our altitude, that gives us a gravitational field that's 2/3 the strength of Earth's gravitational field on the surface. We are going to get now, if you want to, you can go ahead and solve for that square root of 3/2 minus 1 and get a number. And then you could have that number times the radius of the Earth. Either way, it's fine. You get a constant times the radius of the Earth. And this would be, and you would solve this. You could look up the radius of the Earth, plug it in, and you would get the altitude necessary to facilitate this new gravitational field. Okay, let's look at part B. Okay, part B. N equals 1/3. h is going to equal the radius of the Earth. One over square root of 1/3 minus 1. Radius of the Earth. Okay, that's going to give us the radius of the Earth with square root of 3 over square root of 1. Well, square root of 1 is just 1. Okay, and a number over 1 gives us our value. So our altitude for a gravitational field that's 1/3 of Earth's regular gravitational field is going to give us the radius of the Earth, square root of 3 minus 1. And so keep in mind, you're going to be doing some of this as practice for assignments, and we're going to do this in class. Again, it's mathematical derivation. So make sure you go back and you review everything that we did, because we started with some theorems, the idea of a gravitational field. We started with the idea that our new gravitational field is going to be some number times the original gravitational field. Then what we ended up doing was saying, well, we can work on solving for that number. Started here, and then worked our way through until what we really ended up with is we wanted to find out what that value of h is. And so we plugged in the h plus the radius of the Earth and solved for h to get our generalized equation. Then from there, you can plug in your value of n and solve for each individual altitude. And again, if you went from here, you could plug in the radius of the Earth, look up that number, and you would get an actual altitude at which the new gravitational field would be, either n equals 2/3 or n equals 1/3 the original gravitational field of Earth. Okay, let's look at something where we can actually work out and get some numbers. So we have an astronaut stands at a position on the moon such that the Earth is directly overhead and releases a moon rock that was in her hand. What is the gravitational force exerted by the moon on the 1 kilogram rock resting on the moon's surface? What is the gravitational force exerted by the Earth on the same rock resting on the surface of the moon? What is the net gravitational force on the rock? Okay, so let's look up some numbers. You can find these on tables in most physics books. So let's see. The mass of the Earth is going to be 5.97 10 to the 24th kilograms. The radius of the Earth is going to be 6.37 10 to the 6th meters. For the moon, the mass of the moon, 7.35 10 to the 22nd kilograms. Radius of the moon, 1.74 times 10 to the 6th meters. And the distance between Earth and the moon, so of course that's the distance between the center of mass of Earth and the center of mass of the moon, 3.84 times 10 to the 8th meters. Okay, so what is the force of gravity exerted by the moon on the 1 kilogram rock? Okay, well, we can use the standardized law of universal gravitation to figure that out. Force of gravity of the moon, or universal gravitational constant, the mass of our moon, mass of our rock, over the radius of the moon, squared. It's a 1 over r squared law. So this is our theorem. This is our universal force of gravity. So then we can plug in numbers. And then, of course, this would be in your general r hat direction. Okay, so our gravitational constant, 6.674 times 10 to the negative 11th cubic meters, kilograms, times second squared. Okay, mass of the moon, 7.35 times 10 to the 22nd kilograms. Mass of the rock, 1 kilogram, over the radius of the moon, 1.74 times 10 to the 6th meters. We're going to square that. And you put all this into your calculator, and you find out that the force of gravity of uh, of the moon on the 1 kilogram rock is 1.62 newtons in the r hat direction, or the magnitude of that, since you only have the one direction, the one unit vector, your magnitude is going to be the 1.62 newtons. Okay, so part B. What is the gravitational force exerted by the Earth on the same rock resting on the surface of the moon? Okay. Now we're going to have to think about this for a second. So the rock is on the surface of the moon, and we know the distance between the Earth and the moon is measured from center of mass to center of mass. So the distance from the Earth's center of mass to the rock, we're going to call that r, is going to be the distance between the Earth and the moon minus the radius of the moon. And so that's going to be 3.84 times 10 to the 8th meters minus 1.74 times 10 to the 6th meters. And so r, the distance from the center of mass of Earth to the rock, is going to be 3.82 times 10 to the 8th meters. Now, granted, this isn't really changing things a whole lot. You see that essentially we probably could have just used the distance between Earth and the moon. But corrections like this are going to become important as you go deeper and deeper into physics. So it's good to go ahead and get used to them now. Okay, so now the gravitational field. Let's just work with the gravitational field of the Earth, okay? And then we're going to equate that to something we've been using, the force of gravity or weight. Now, if you wanted to continue with this and just go right to the universal law of gravitation, fine. But I want to walk it through the gravitational field of the Earth at the rock. Okay, so our theorem is the gravitational field of the Earth is going to be G mass of the Earth over r squared. So that r we just calculated, you could abridge this to say G mass of the Earth over the distance between Earth and the moon minus the radius of the moon squared. So you could do that, but we already have that number, so we'll just plug it in. And so this is going to become at the rock, or at the surface of the moon, we're going to have, so G is our 6.674 times 10 to the negative 11th meters cubed, kilograms second squared. And then the mass of the Earth, 5.97 times 10 to the 24th kilograms over, and then our radius to, so our distance from Earth to the surface of the moon, 3.82, 10 to the 8th meters squared. And this gravitational field is going to come out to be 2.73 times 10 to the negative third. Okay, now, when you're going through and you're looking at your units, so you can see that kilograms and kilograms are going to divide out. Meters squared is going to take care of the cubed, and you'll have meters left. You end up with units of meters per second squared. So this is what we're talking about when we say that gravity is an acceleration. So this gravitational field measures as an acceleration. You'll see some other units for it here a little later, but just know that gravity is an acceleration. Most of the times you see when you're working out problems, at least kinetic problems, you're going to be using, which is the gravitational field at Earth's surface. So that's just a number you'll get used to. You're going to use it a lot. But so what we've calculated here is the gravitational field at the surface of the moon. It's very, very small, but it's still there. Okay. And so, I mean, you have the magnitude. We could also vectorize it. Now, we've been talking about force of gravity and and weight. So what is the force of the Earth's gravity on the rock? Okay, so our theorem for this force of gravity is mass times gravity. So I wanted to walk it through this way because you're going to see this theorem a lot. So take, for example, when you have a free body diagram and you're thinking about the weight of the mass you're looking at, well, that's mass times gravity. Weight is the gravitational force. So it kind of helps just to start getting used to the format. So that means the force of gravity on the rock is going to be 1.0 kilograms. But you notice here, you could just take the mass of the rock and plug it back in the gravitational field, and you'd end up with the gravitational law. So we have our 1.0 kilograms times 2.73 times 10 to the negative third meters per second squared. Our hat. And what we're going to get when we put these units together, we're going to get kilograms meters per second squared, which is a Newton. And that's going to be directed towards the Earth. Okay, so that's the amount of force that the Earth is putting on the rock when it lays on the surface of the moon. Now, what is the total force exerted on the rock? So what we're looking for, so our theorem, the net force going to be the sum of the forces on the rock. In this case, that's going to be the force of gravity exerted by the moon plus force of gravity exerted by the rock. And then we have to think about what we're going to do is we're going to call towards the moon the positive direction. And so that means the force of gravity towards the Earth is in the negative r hat direction. So then what we can say, this is going to give us so force of gravity of the moon, r hat, minus force of gravity due to the Earth, r hat. So it's a negative r hat direction. So it's the gravity exerted by the moon minus the gravity exerted by the Earth. Okay, so now we can plug numbers in and solve for this. So again, we have our theorem. We switch it up to the equation we can plug numbers into. This time, the variable we're solving for is already solved for, the total force. And then we put in 1.62 newtons, r hat, minus 2.73 times 10 to the negative third newtons, r hat. And you find out that really the force exerted by the Earth doesn't really do anything to the rocks. You end up right back at about 1.62 newtons r hat. Or if you want the magnitude of this, let's just look at the entire theorem here. Oh, we're not really doing X or Y. Yeah, so we're not breaking this into X or Y. I don't really want to go start confusing people. So when you have a vector that has only one direction, the magnitude of it is simply that number, because it's if you start thinking of this in terms of components, if we look at, for example, we say well, that's not the moon. Let's say we have the moon here, and we can say we have a couple of components where you have your rock, and you can say, well, you have that component, and maybe you have that component, that's Y, that's X. Well, the r hat direction, they both point in that direction because they're going towards the center of mass of the moon. So you see you have nothing in the X direction. So if you said, it's going to be 0 plus 1.62 newtons squared, square root, and you end up with the total force of 1.62 newtons towards the moon. So again, if you have a vector that where the only thing in the vector component form is a singular direction, a singular unit vector, the magnitude of that vector is going to be the number that you see there. In this case, it's the 1.62 newtons r hat direction. You can break it down into X and Y if you want to, but you notice that one of the components will be 0. And in this case, J hat and R hat pointed in the same direction. And so the magnitude of the vector is just going to be the 1.62 newtons. Okay. Okay, gravitational fields. So we've been talking about gravitational fields. Let's think about where that comes from. Okay, so object on the Earth's surface. So again, we've been talking about weight, and we use this formula above. Gravitational force is going to equal your weight, which is equal mass times gravity. Now, the gravity we said that's going to be used, the gravitational field, is going to be about 9.8 newtons per kilogram. So it's 9.8 newtons of force for every kilogram of the mass, or the 9.8 meters per second squared, which is an acceleration. Okay, so let's think about, and if we know that the format, is mass times gravity. Let's look at the universal gravitational law. Okay, so what we would have is the mass of the object we're looking at times the mass of the Earth over the radius of the Earth squared in the r hat direction. Now, what I'm going to do is pull that mass out front because, again, it's just multiplied in there. I'm going to separate off the g, mass of the Earth. Okay, we have that. And if we compare it to, the fact that the gravitational force equals mass times gravity, that means the gravitational field vector, or the gravitational acceleration is going to have to be g, mass of the Earth over r e squared. So again, we've been using that format, but this is where it comes from, at least this is how you can get to it. Not a difficult derivation, but it's nice to think. It's good to start thinking in these terms so that you can use them later on. Okay, let's start looking at contact forces. So contact forces, again, the normal force is one of them, friction is another one. These have to do with an object coming into contact with another object. And so what forces occur when that happens? So like friction is caused when two objects try to slip past each other, but it only occurs when they contact each other. Normal force, again, if you set something on a table and it doesn't fall through, your gravitational force on the mass uh, produces a force pair, so the gravitational force, and it produces a normal force that presses back on the object. So the table pressing back on the object is your normal force. So let's I don't know, let's use that idea. So let's look at normal force. So we just have a mass sitting on a table, and we know that we're going to, there's the center of mass. We know there's going to be a gravitational force. Gravitational force or weight. But the object's not moving, so the object contacts the table, but it doesn't continue to fall through. That means the table then pushes back with a force we call the normal force. And that's going to be produced when the object makes contact with the table. But what happens, like, let's start getting used to the idea of what happens. Like, let's say this mass is on a slope. Okay, so we're going to try to make this as nice as possible. Okay, so our mass is on a slope. Now, let's think about what our normal force might look like here. Again, we're going to have our center of mass. Now, gravitational force is always going to point straight down towards the center of the Earth. So, gravitational force is going to point straight down. Okay, but your normal force is always going to point perpendicular to your surface. So, normal force is going to go off in this direction. Okay, so, and again, one thing we could do here is set our x and y. Oh, let's see. That's going to be our x. So then our y, your normal force lies directly on the y. Okay, and then we can start analyzing the gravitational force. So it's like, what produces the normal force in this case? Well, we now see that our force of gravity is going to make an angle theta with our y-axis. And this is going to give us components. So I think I need to move this out of the way. Okay, so our components. There's one of them. There's the other one. Then we could find those components analyzing the right triangle, like we have so many other vector components. But you can see that the normal force this time is produced by the y component of the gravitational force. Okay, should probably make this a little more clear. Gravity y, gravity x. So the normal force is not going to be the same size as the overall gravitational force. It's only going to be as large as the y component. Don't worry about this. You're going to use it a lot, and so it'll make sense as time goes on. Another contact force is going to be friction. Okay, so this will come up later, but I want you to start to get the idea that friction is a non-conservative force. So, I mean, if you take two things and you rub them together, one thing that you notice is you tend to get heat. So energy will leave the system through friction. Now that's really going to it's really going to be your kinetic friction, but we'll work with it as time goes on. So you have two types of friction: static friction and kinetic friction. Static friction is strong enough that two objects they're contacting each other, and they're trying to move like slide past each other, but they can't. They don't actually move. So that friction is called static friction because the two objects are not sliding. Uh, the kinetic friction is when two objects start moving and sliding past each other. You still have friction trying to prevent that sliding, but the system is still moving, so that's called kinetic friction. Now, they're both going to take a similar format. Your static friction is going to take a format of mu sub s multiplied by the normal force. So whatever the normal force of your object is, your mu s is going to be your coefficient of static friction. Okay, and that's the Greek letter mu. And now, when you use this equation, that is a maximum static friction force. Okay. However, when you're looking at kinetic friction, again, you have the same format, mu sub k, so that the coefficient of kinetic friction times multiplied by the normal force your object produces. However, this is not a maximum force. So just kind of keep that in mind. Static friction, this equation is a maximum for static friction, not a maximum for kinetic friction. And you'll notice that kinetic friction is usually quite a bit lower than static friction if you look up various graphs. But a way we can think about this is let's just look at two free body diagrams. Okay. Okay. Now let's start looking at the forces involved. So this is going to be our static system. So no velocity, it's not moving. However, we do have an applied force trying to move the entire system that way. Okay. Now we know we have a gravitational force, and then the reactionary normal force. But however, this system is not moving. There's no velocity. So the applied force is trying to move the object to the right. However, we have a friction force. And again, I draw them this way. You can draw your friction force all the way over to the center of mass. That'll be fine. But you have a friction force, a static friction force, that is preventing this object from moving due to the applied force. That's our static system. The system is going to look the exact same way. Well, so let's just make it easy. Yeah, we're actually going to shorten that vector a little bit. Try to get across the idea that this the friction's still there, but it's not strong enough to actually stop the applied force from moving the object. And so, of course, what we have is we have a velocity in the direction of the applied force. So you can see that the object is not moving in one situation, it's moving in the other. The friction force is going to go opposite the applied force, and that's going to become nuanced when forces are applied at angles, but still, it'll make sense. So the way you can think of it here is static is not moving, kinetic is moving. Okay. So let's say we have a car moving, it's speeding up to pass a truck on a level road. The combined contact force exerted on the road by all four tires. So we're not going to have to look one tire at a time. We're taking this as a whole object, and the total exerted contact force is going to be 11.0 kilonewtons downward, with a horizontal component of 3.3 kilonewtons southward. Okay, so let's think about what happens when a wheel contacts the road. Okay, so we have our wheel. It is rotating. So at each individual point, you're going to have a vector. That's perfect. It's going to be a tangent line from the curvature of the motion. So when it hits the road, the force of the wheel on the road is backwards. So again, and if we say that that way is south, that is our 3.3 kilonewtons southward. Now, what this is going to do is it's going to produce a friction force. That's not going to work. It's going to produce a friction force in the other direction. So the contact force, the wheel against the road going south, is going to produce a friction force going north, and that friction force is what's going to propel your car forward. Take some time to think about it, wrap your mind around what's happening here. And we call it static friction because, again, if this wasn't static friction, your wheel would just be spinning against the road, and we don't want that. So we want to be dealing with static friction, and that static friction force, which is going to be equal and opposite, because again, it's static, equal and opposite to the contact force. That's what's going to move your car. So we also have a drag force on the car. So let's look at a free body diagram on what's happening to this car. So we're looking at all the forces on the car, okay? So that contact force that we talked about, that was the wheel applying force to the road. The friction force is the road applying force to the wheel, which is of course force to the car. And so what's going to happen is we are going to get a static friction force going that way. We are going to get a drag force going that way. So against the car, I'm just going to call that drag. Let's see. We are going to have the gravitational force of the car, and then exerted back on the car, we are going to have a normal force. So again, all of these can be viewed as forces on the car. So the gravitational force may be pressing into the road, and then the road presses back with the normal force, but the gravitational force is the force of gravity on the car. The normal force is just what the road applies back, so that the car doesn't fall through and just continue on falling through into the earth. Okay, so that is our free body diagram. Okay, so okay, that means, and again, we'll mark north, south, because that can help us later on. Okay, B, what is the weight of the car? Okay, well, this one's kind of a logic. This one's logic. So we know that our force of gravity, it's only applied in one direction. So it's the force of gravity in the j hat direction. And we know that what we know is that we're going to call that downward direction negative. And we know from the problem that all wheels pushing down on the road exert a force of 11 kilonewtons. So that means we have a negative 11 kilonewtons j hat. And again, all of the forces applied only in one direction, which means that the magnitude of the gravitational force, or the weight, is going to be 11.0 kilonewtons downward. Okay, so that is the weight of the car. Part C, what is the net force acting on the car? All right, well, let's start with our theorem. Okay, so overall, we're going to have our frictional force, our drag force, our normal force, and our gravitational force. Okay, so that's our theorem. So what we really want to do is we can break this apart into x and y. So let's look at the sum of our forces in the x direction. That's going to be our frictional force plus our drag force. Now, if we think about this, so we have a plus x and minus x, plus y, minus y. So we really set our directions like we would on a Cartesian coordinate system. So that means the frictional force is going to be That's going to be a positive I hat minus the drag force I hat. So it's going to be F minus S. And so what we're going to get here is we have, well, we know that the frictional force, since it's equal and opposite, and we know that the contact force is 3.3 kilonewtons southward, we know that the equal and opposite force, the frictional force, has to be 3.3 kilonewtons northward. Then minus your drag force, which was 1.2 kilonewtons, I hat, and you see that you get a magnitude of 2.1, well, you get a vector of 2.1 kilonewtons in the positive direction. Okay, now let's look at the sum of our forces. In the y direction, that's going to be our normal force plus our weight, the gravitational force. We're not actually going to need numbers for this, because if you think about it, the car's not falling through the road. So the gravitational force and the normal force cancel each other out, which means normal force equals negative force times gravity. And so I can say minus force of gravity plus the force of gravity equals 0. So there's nothing happening in the j hat direction. Now, again, you could just look at these as magnitudes, and you can see that the only direction that's going to have any force is going to be in the positive x direction. Let's go ahead and look at the total force in terms of the addition of all of these vectors. That is going to be 2.1 kilonewtons I hat plus 0 j hat. 2.1 kilonewtons I hat, or, and again, all of the forces applied in one direction, so the magnitude is just that number. And that's applied in the northward direction. Okay. Again, if you want to see that magnitude, oops. And for this one, we would have our 2.1 kilonewtons squared plus 0 1/2 equals 2.1 kilonewtons. So again, 2.1 kilonewtons north. Okay, so that's how we really go about solving a problem like this. All right, let's continue on. Equilibrium on an inclined plane. So again, equilibrium, sum of all your forces equals 0. So let's go ahead and look at our inclined plane. Okay. Maybe not be giving myself enough room. That's okay. I'll move it. Okay, so we have a mass on a plane. Yeah, I'm going to go ahead and give myself a little more space here. There we go. Going to mark my center of mass. Okay, now I'm going to go ahead and mark. I have an angle phi. Let's look at our gravitational force. Gravitational force, we know the normal force is perpendicular to the surface. Okay. And we have an applied force. That's just going to be a force pulling on the mass, trying to move it up the ramp. But we have a couple of other things going on here. Okay, so right, I have an x and a y. That x component can also be seen up here. Okay, we're also going to need to make note that we have an angle in here. Going to call that beta. And then we're going to need one more angle. We call that one alpha. Okay, so let's start taking a look at this. The total force of this system we're going to get our force of gravity plus the applied force plus our normal force equals 0 because it's in equilibrium. And if you look careful, we're not taking into account components yet. So those are the only three forces applied to this mass. Okay, so let's start looking at our components. Our force, our gravitational force in the x direction is going to be the gravitational force cosine of beta because, wait, yep, did that backwards, sorry. Sine of beta, because the gravitational force is opposite the angle beta, so it's sine. Now, we also remember that force of gravity is your weight, remember? So that's going to be mass times gravity sine of beta. Now let's look at our force, our gravitational force in the y direction. It's going to be gravitational force cosine of beta, or mass times gravity cosine of beta. Okay, our applied force. So what we're going to do is we're going to mark positive x and y in those directions. So this means we have a negative magnitude of our force, I hat, because the applied force is in the negative x direction. Our normal force is going to be in the positive y direction. So let's go ahead and start adding these together. Okay, so let's go ahead and write our gravitational force in vector component form. Okay, that's going to give us mg sine of beta I hat plus mg cosine of beta j hat, and now okay, so we're going to add together all of the I hats. Plus, then we're going to add together the j hats. Oh, I gave you a wrong sign. That's negative. Let's talk about y. Look at the direction of the y of the gravitational force in the y direction. That's going to be the negative y direction. So sorry about that. You got to put the negative sign in there for the y direction. Now we're going to have normal force minus g cosine of beta j hat. That's our net force right there. This is going to equal 0. So another thing we can do is we can break this into x and y. And each one of those components is going to equal 0 because, again, it's not moving in the y direction. It's not moving in the x direction. So it's in equilibrium in those directions. X components, mg sine of beta minus the applied force equals 0. So force is in the y direction. Normal force minus the y component of the gravitational force. And then, let's say, for example, you were only given angle phi. Can we end up relating, because these are all in terms of beta right now, can we end up relating this to phi through beta? Okay. Well, if we think about our triangles, and you can look at the free body diagram to see this, 180 degrees, all the angles of a triangle add up to be 180 degrees. That's going to be phi plus alpha plus 90 degrees gives 180. And then we can also say that if we look, alpha and beta share a 90-degree angle. Which is right there. So alpha plus beta equals 90 degrees, or beta is 90 minus alpha. Oh, hang on. Let's do that the other way. Alpha is 90 minus beta, which we can then plug in. So phi minus beta plus 180 equals 180. So we have 0 equals phi minus beta, or beta equals phi. So what we can do with our component equations, with our x and y directions, we can just plug in phi. And again, we can calculate anything we need from there. So we can end up with, let's see, our x components. We're also going to get mg sine of phi minus f equals 0. Our y forces, normal force, mg cosine of phi also equals 0. So again, we can relate these to almost any angle that we see there on the slope. Now this is quite a bit of a workup for really just kind of first getting to this. This will be something we practice a lot, so you'll get more used to it over time. The whole point is seeing how you can really work these various systems. So again, you have a mass on a slope. It has an applied force, a normal force, a gravitational force. How do we really deal with the components involved there? And, based on what angle we're given, how do we really work through that to figure out what we might need to know? Because in this case, for example, you could figure out, if you're looking at y, you could figure out the magnitude of the normal force because it's going to equal the y component of the gravitational force because you probably know one of those angles. Okay, so let's say here during a baseball game, groundskeepers drag mats across the infield dirt to smooth it. A groundskeeper is pulling a mat at a constant velocity. So again, no acceleration. So that means there's constant velocity. You have an equilibrium system. So no net force. If you have a positive net force, you have an acceleration or a positive magnitude, which is again redundant because anyway. So it's moving at constant velocity by applying a force of 120 newtons at an angle of 22 degrees over the horizontal. The coefficient of kinetic friction between the mat and the ground is 0.60, so it's dragging along the ground, is creating friction. Find A, the magnitude of the frictional force between the dirt and the mat, and B, the weight of the mat. Okay, let's start with a free body diagram. Okay, we have our center of gravity. Let's see, we're going to have an applied force. And you can draw it from the center of gravity. I like to draw them out here because I'm going to work with components, and I just think it makes it easier. That's our applied force. We are going to have a weight. Just think of all the things that equals. It's going to be an equilibrium in the y direction, so we're going to have a normal force. We know it's moving at a constant velocity. We're not going to worry about that vector, but it's just, I'm going to denote it because that's what's happening. And then there's going to be a frictional force. Going back that way. Because the mat is going to be moving in the direction of the applied force, so the frictional force will be the other way. And then what I'm going to do is I'm going to set myself some x and y axes. I have x and y. I have an angle theta. And so I know I'm going to have components fx and xy and fy. So this is really my free body diagram that I'm looking at here. So I know that the magnitude of the applied force is 120 newtons, and theta is going to be 22 degrees. The coefficient of kinetic friction is going to be 0.60. So let's start the magnitude of the frictional force between the dirt and the mat. Okay. So the frictional force is really a force in the x direction. So let's look at that. Sum of forces in x. Now again, all of these directions are in equilibrium because there's no acceleration. So the sum of forces in x are going to be the x component of the applied force plus the kinetic friction force equals 0. That's my theorem. However, my positive x is to the right, so my frictional force has a negative I hat. So then this will translate into my f of x. Guess you could say there's an I hat there too. Okay, minus fk equals 0. And what we end up with is your frictional force is going to be equal to the x component of your applied force. Now, it may seem that since this applied force x component is equal to the frictional force, that the mat shouldn't be moving. We'll deal with that later on. You to get something moving, you have to reach a maximum force that will overcome static friction, and then the entire system drops down. And so then the force applied to actually keep the mat moving at a constant velocity is going to be overall less than the force to get the object moving in the first place. But since it's a constant velocity, we still have an equilibrium system, so they have to be equal to each other. But again, it'll make more sense as time goes on. Okay, so let's think about what our x component is. Okay, well, we see that the x component is adjacent to theta. So this means we're going to have the magnitude of the force, cosine of theta, for the x component. That's 120 newtons, cosine 22 degrees. And our kinetic friction force is going to be about 111.3 newtons. Okay. So let's go look at part B. What is the weight of the mat? Okay. This is dealing with forces in the y direction. Sum of forces of y and y is going to be my normal force plus my weight plus my y component of my applied force that equals 0. And so we know, so that's my theorem. And so then that's going to be my normal force in the positive j hat direction, my weight in the negative j hat direction. The y component goes in the positive j hat direction. That equals 0. So then I can solve for, and then the j hat can drop off because we can just deal with these magnitudes because they're all in j hat. Minus weight equals a minus normal force minus the y component, multiply through by -1, normal force plus my y component. And now I've solved for the variable. I have a couple of things that I need to plug in here. So we know that kinetic friction is the coefficient of kinetic friction multiplied by the normal force. And so my normal force is going to be my kinetic friction force divided by its coefficient. And then, of course, my y component, I see my y component is opposite my angle theta, so it's going to have to take on the sine function. And I'm going to get frictional force over the coefficient of kinetic friction plus the magnitude of my applied force, sine of theta. And now I have an equation I can plug numbers into. Weight is going to be 111.3 newtons over 0.60 is my coefficient. 120 newtons, sine of 22 degrees, and my weight comes out to be about 230.4 newtons. Okay, now, this is going to end what we're going to talk about for today. You're going to want to go back and review some of this math. It's all stuff you've been doing, but we're putting it together in bigger and bigger formats now. We brought in some new equations like our friction equations. And really, we're just looking at situations, and you see how important drawing the free body diagram is. The free body diagram places your vectors on your object so that you can begin to analyze everything in the x and y direction. You set a positive x, a positive y, and you just start working out what you have. You remember things like an equilibrium system means the sum of your forces is 0. A constant velocity is an equilibrium system. So you just kind of keep little things like this in mind. And so have a good weekend, and I will see you next time.